So I will be speaking about a classical elliptic inverse problem in the anisotropic setting. So I will be concerned with the recovery of a potential in a Schrödinger equation with a Laplace-Beltrami operator on a compact manifold. And there will be several structural assumptions that I will be making on the metric. So this is a joint work with Slava Kurilev from the University College London, Matti Lassas from the University of Helsinki, and Mikko Salo from the University of Jyväskylä. So I will start with a sort of prologue in the Euclidean setting. I will explain one way of constructing solutions to the Schrödinger equation. And this is actually helpful for the Calderon problem in the Euclidean setting with partial data. So there has been some interaction between the geometric problem and the problem with partial data. So as a prologue, I will do a very short construction which will show some of the features of what will happen in the geometric setting. So my aim in this, with this starting point is to construct solutions to the Schrödinger equation, so on a bounded set in Rn. And I'm mainly concerned with the case of dimension bigger than 3. The potential is just an L-infinity function. And the method is the classical construction by complex geometrical optics, which was introduced by Sylvester and Ullmann, with linear weights. And what I want to show here is how the construction can be done with nonlinear weights and sort of the geometric decomposition which appears there. And so this will be closer to what was done by Koenigsröstrand and Ullmann in the partial data case, and is useful in the sense that it allows to obtain stability estimates as well. So this will be a sort of an example that you can have in mind of the structural decomposition which will be made later on on manifolds. So you can see Rn as a sort of product of the real line with the sphere, and this is just the classical, the standard polar decomposition of variables. So I'm picking x0 to be some point outside of my bounded set omega. I'm taking the radial variable, the norm of x minus x0, and taking t as the log radial variable. This is classical. And then you have the angular variable. I'm not sure this is, yeah, the angular variable here. And I will explain in a minute what this is. This is actually a cap on the sphere. And if you compute the Laplace operator in those coordinates, you end up with a very simple operator. So there is some conjugation with exponential weights, but mainly you have something which look like second derivative in the log radial variable and then some modified Laplacian in the angular variable. So the feature here is that you can sort of solve the Schrödinger equation or just look for harmonic functions as which are tensor products of the log variable and the angular variable. Yeah, so I should explain what this. So in the particular case where x is varying in a bounded set, the angular variable varies only on a cap of a hemisphere which is strictly smaller than the northern hemisphere. And so the particularity of those caps, so this is just the cap with colatitudes much bigger than alpha 0. And the interesting feature of those caps is that these are simple manifolds. And I recall that simple manifolds are compact Riemannian manifolds with boundary, whose boundary is strictly convex, and for which the exponential map is everywhere a diffeomorphism. So in particular, you have no conjugation point problem. So of course, if you take the whole hemisphere, this is not true, because points on the boundary have a lot of conjugate points, which are the antipodal points. But if you take something strictly smaller, then this disappears. So you have to think that now you can look at Rn as a sort of product of an Euclidean line, where you have an Euclidean variable, which is this t variable, this sort of time variable, log radial variable, and some angular variable which varies in a simple manifold. So the particularity of simple manifold is that on those manifolds, a specific transform, which is the geodesic ray transform, which will appear later on. So this is just like the usual X-ray transform where you integrate functions on lines. On a manifold, you just integrate functions on geodesics. And on simple manifolds, it is known that this geodesic ray transform is injective, and also that you have stability estimates. And this is very useful. So going back to my construction, so you can look at first approximate solutions, approximate harmonic solutions, or approximate solutions to the Schrödinger equation. And as I said, I'm using sort of separation of variables. So I'm taking a solution to a second order differential equation in the t variable and another function in the angular variable. And then I have a sort of complex parameter which sort of measures the frequency. And what is important is that you have to think that these are exponential increasing or decreasing depending on the sign I put here, functions. And the tau parameter is going to be large. And lambda is another parameter which is useful. So now if you want to solve the Schrödinger equation, one way of doing that is to look for what is known as Quasimodes, here for functions, Vs. And these are like generalized eigenfunctions, except that instead of asking this to be 0, you just ask this to be a bounded function or a decreasing function in the tau parameter. Okay, so, but you can think of this as being sort of generalized as eigenfunction. So with this choice of function u, if you compute the Laplacian with the computation I did before in the polar coordinates, this is what you obtain. And this, since this is bounded, you obtain that this remains bounded. And of course, you can always improve the decay here in terms of tau. So why is it an approximate solution? It is because when the Laplacian falls on the exponential, you expect that this is going to decay like tau square, and you obtain something here which is bounded with respect to tau. So it's better than the expected decay, and in that sense it's an approximate solution. And as I said, in a general situation you can have negative powers of tau here, but this is not needed in the inverse problem. Okay, so how do you construct those Quasimodes? Well, you can go back to your hemisphere and there also consider polar coordinates on the sphere. So you can take theta to be the distance to a point which is on the equator. And this will be like the colatitude with respect to this pole y. And then you have this sort of radial variable, which is now theta, and an angular variable eta, which varies now in an n-2 dimensional sphere. Okay, so in dimension 3, this is another angle. And I guess in dimension 3, it's just the classical way of parametrizing the sphere. So the important thing is, once again, you have a sort of conjugation factor which comes from the expression of the Laplacian, of the spherical Laplacian. And the important thing is you have an exponential with respect to the angular variable, and you can take any function here of the remaining angular variable. So this is a Quasimode in the sense I've shown before. You can compute the Laplacian and you obtain something which is bounded with respect to tau. So remember, S is tau plus I lambda. So this is highly oscillating in tau. Okay, so once you have approximate solutions, they can actually be upgraded to exact solutions, and I will talk a little bit about that. And this is due to a priori estimates that you can have on the Schrödinger equation, and these are known as Carleman estimates. So the thing is, you think of your Schrödinger equation as a sort of perturbation, where the potential is small when the frequency parameter tau is large. So you can construct exact solutions of the Schrödinger equation of this form, plus something which is small with respect to tau. Okay, so this will become clearer later on in my talk, but now I'm going to consider a special object which is related to the inverse problem I will be studying, which is this integral here. So I'm interested in products of such solutions, and I'm taking solutions which have antagonizing exponential behavior. So if you look at the product, the exponential growth will cancel out. Okay? So if I look at this integral with a potential q, and I compute this integral, this is what I get. So as I said, the real part here will cancel out. Remains some oscillation due to the imaginary part of my complex parameter S. There are some functions coming from the change of variables. And if you look at what you get, with respect to the log radial variable, you get the Fourier transform basically of this function q. And then you have the product of those Quasimodes and something small here. So now if I pass to the limit when tau goes to infinity, I get just the first term here. So this sort of exponential, this Fourier transform with respect to the t variable. And then this is exactly what I get here with the exact expression of my Quasimodes. So what you get inside here, so there's an exponential factor here that you can forget. Let's say that lambda is 0. And then what you're doing is you're integrating this Fourier transform with respect to the t variable on big circles on the sphere, so on geodesics. So what you get here inside is up to this exponential factor, the geodesic ray transform of this function. Okay, so this is an attenuated X-ray transform because there is this attenuation factor. And because you can freely play with this function b, then from the knowledge of this integral, after passing to the limit, you have a knowledge of the attenuated X-ray transform and up to some function b here. So what I'm saying is that with this construction, from the knowledge of this integral, you get a knowledge of the attenuated X-ray transform. So you have a sort of mixed transform, which is a Fourier transform in the log radial variable and this attenuated X-ray transform in the angular variable. So with the result I was saying, because you're working on a hemisphere which is strictly smaller than, a cap which is strictly smaller than the hemisphere, you know this transform to be injective, so you can actually recover the function q. And this is actually known when you have an attenuation which is small. So that means that you have an information on the Fourier transform of this function q when lambda is small. And then by standard unique continuation techniques, you can get information on the potential. So this is a sketch of the construction which is partly done in Koenig, Schröster and Ullmann's paper. And you can obtain actually precise stability estimates on the Dirichlet-to-Neumann, on recovering the potential from the partial Dirichlet-to-Neumann map. So let me just say that here this denotes the Dirichlet-to-Neumann map measured on a small set of the boundary, and you have some log-log stability using that. And this is a joint work with Pedro Caro and Alberto Ruiz. And so that was just a pretext to introduce some of the ideas which will come up later. That is a sort of decomposition of the space Rn, which will be transformed, or omega rather, the bounded set, as a specific product of an Euclidean manifold, which was this T variable, and another manifold, which is a compact Riemannian manifold. And then this construction using complex geometrical optics with an exponential part and Quasimodes on the transversal manifold part. So the transverse, you can think of this of the sphere. Yeah, maybe I can just. Okay, so let me now continue with the problem I have in mind, describe it in more details, and then I will come back to the different things that I've sketched here in a more general context. So this is a well-known inverse problem well-known inverse elliptic inverse problem, and I always like to put this picture of Calderon, which I like very much. And so this is a problem which was formally stated in the 80s, and the question is whether you can determine the electrical conductivity of a body by making current and voltage measurements at the boundary. So I'm going to to cheat slightly and give a geometric formulation. So this would be in the case where the conductivity depends on the direction. I don't want to write the conductivity equation. I want to go directly to the equation that I'm interested in. But let's say that there are known reductions from one to the other. So I'm considering a compact Riemannian manifold with boundary, and everything is going to be smooth. Okay, so the challenge here is to go from analytic to smooth, and then going lower in irregularity is extremely complicated, well, I guess even in the Euclidean case. And I will be interested in the case of dimension n bigger than 3, as this problem in dimension 2 is solved. And I guess there are many questions now which are solved in dimension 2. So Q is just is going to be a bounded measurable function. I'm looking at the Dirichlet problem with the Schrödinger equation. So the measurement is going to be modeled by the Dirichlet to Neumann map, which sends to a Dirichlet data on the problem the normal derivative of the function at the boundary. And I guess this should be an F here. Okay, and U is the exterior unit normal to the boundary. So in the talk, the inverse problem will be to find Q from the Dirichlet to Neumann map lambda GQ, and G will be fixed, and there will be a lot of assumptions on the metric G. Okay, but the general problem, of course, is to try to recover the metric from the Dirichlet to Neumann map. Okay. And I guess it's missing here. Okay, so the general problem is quite complicated, and in particular you have to deal with the fact that there's a gauge invariance in the problem. That is, if you pull back the metric by a diffeomorphism, which is the identity on the boundary, then you don't change the Dirichlet to Neumann map. So the general inverse problem has to be reformulated modulo those isometries on the compact manifold. Okay, and for those who are interested in the conductivity problem, so there's a very simple way of going from the conductivity equation to this geometrical case in dimension n bigger than 3. In dimension 2, these are two different problems. Okay. Okay, so it's known that there is another sort of well, it's not exactly a gauge invariance, but there's another conformal gauge transformation, and that is when you change the metric by a conformal factor, then you just change the equation by changing the potential, okay, up to some conjugation by the conformal factor, and this translates also on the Dirichlet to Neumann map. So in particular, if you know the conformal factor at the boundary and its normal derivative, you can always go from one Dirichlet to Neumann map to another where you have changed the conformal factor. Okay? And of course, knowing the metric at the boundary is now a classical and well-known problem, which is known as boundary determination. and was first observed by Kohn and Vogelius for the conductivity equation, and by Lee and Ullmann in the geometric setting. And this is the starting point of solving the problem for analytic conductivities, because from that then you go to inside with unique continuation. So if you look at the general inverse problem, what is known now is the Euclidean case. So when G is the Euclidean metric, and sort of a reasonable inverse problem in between is the case where you look at this general inverse problem in a conformal class of metrics. And this is reasonable for several reasons. One is that you just have to find one function, and the other one is that in the conformal case there is no gauge invariance, meaning that the diffeomorphism has to be the identity. There is no diffeomorphism isometry between two conformal metrics, which is the identity on the boundary. Okay, so this is sort of an intermediate step, and already this one is a very complicated problem. So some references. So mainly what is understood is the analytic case, and is based on this boundary determination, which is due to the fact that the Dirichlet to Neumann map is a pseudo-differential operator whose symbol you know, and that you can compute in terms of the Taylor expansion of the metric at the boundary. Okay, so maybe I should point out, so in the geometrical setting, this was used by Lee and Ullmann, so this boundary determination result plus some unique continuation, and there you can determine the metric. There were some assumptions which were removed by Lassas and Ullmann. And then there's a specific case also studied by Guillermo and Sabaretto, where they look at the case of Einstein manifolds, which are analytic but not up to the boundary. And there also it's based on a unique continuation argument. So I mentioned also the result of Sylvester and Ullmann, which is the starting point of this whole theory, and in particular of the construction of solutions by complex geometrical optics. And this is the method which is going to be used here. And then, as I said, because of the interactions with the anisotropic setting, the paper of Koenig, Sjöström and Ullmann, which dealt with the partial data case, but where some ideas were already introduced, presenting the construction of complex geometrical optics solutions in a sort of more general setting. And then there's a paper where we dealt with the studied this problem with assumptions on the metric and with some simpleness assumption on the transversal metric, and where we showed also that the method has some inherent limitation. I mean the complex geometrical optics method, in the sense that it sort of imposes some structure on the manifold, and this sort of product structure. And then we were interested also in the case of unbounded potentials, where you have LP Carleman estimate. So what I'm going to talk about is some improvement of this result, where we try to remove the simpleness assumption, so the one that I've showed you on the cap, on the transversal part of the manifold. Okay, so the analytic case is fairly well understood. So really the smoothness is, even infinity metric is the case, is a challenging problem. As I said, there are limitations. So due to the fact that you're using those complex geometrical optics solutions with antagonizing exponential behavior, and this is unfortunate because it means that in the general setting, you have to come up probably with new ideas. And as I said, I will be interested in the recovery of a potential. So the metric is fixed here. I know that the Dirichlet to Neumann map are equal, and I want to show that the potential are equal. And this with boundary determination and the conformal gauge transformation will imply also the problem where you try to find the conformal factor. So in that sense, it's some answer to the anisotropic Calderon problem. And then you can go to the conductivity equation also. Okay, so what is the problem? How does it relate to solutions to the Schrödinger equation? Why did I do this in the prologue? Well, it's a very simple observation, which is based on the on Green's identity, is that if the Dirichlet to Neumann map coincide, well, then you can compute this integral that looks very much like the one I've. Maybe there was no bar here in the prologue. Okay, so you compute this quantity, use the Green identity, and what you get is on the boundary the difference of the Dirichlet to Neumann map. So if they are equal, this is 0, and so now you have to from the observation or from the knowledge that this integral vanishes, you have to deduce that Q1 equals Q2. Okay, and this is for all pairs of solutions to the Schrödinger equation. So you can see that as a density problem, and which can be restated. If I look at the linear span of products of solutions to two different Schrödinger equations with two different potential, is this dense in some functional space, L1 if you take Q to be L infinity? Is it dense in there? Okay, and so that means, well, you have to construct explicitly, or the more explicitly you can, solutions in such a way that you can deduce from the information that this integral is 0 that Q1 equals Q2. Okay, so the aim now is to construct exactly in the way I've described in the prologue, solutions to the Schrödinger equations, and exactly as in the prologue, when you'll have solutions which depend on a large parameter, and when you take the limits with respect to this large parameter, you'll obtain some transform acting on Q1 minus Q2, which is going to be a Fourier transform in some Euclidean variable and a geodesic ray transform in the transversal variables. Okay, so now I guess I need to talk a little bit about the structure I'm going to put, and I'm going to talk a little bit also about the fact that you need this product structure. So what generalizes the decomposition I did in the prologue is the notion of warped products. Okay, so the manifolds I'm going to consider are sort of products of some, so they are going to be compact Riemannian manifold with boundary, which are embedded in some cylinder of an Euclidean part. So the T, as in the product, will be the Euclidean variable. And another part, which is just any manifold M0, G0. And the metric that you're putting on this manifold is a product metric, in the sense that there is this Euclidean part, which is the Euclidean metric. The other metric G0, so which depends only on the transversal variable. So transversal manifold will be my M0, G0 part, and the transversal variable will be the corresponding one. And the only thing I'm allowing is a warping factor here, depending only on the T variable. Okay? And because of the conformal gauge transformation that I mentioned in the introduction, you can look at metrics which are conformal to such warped products. Okay? So this will be the structural assumption, is I'm going to look at metrics which are conformal to warped products of an Euclidean part and another curved part. So the reasons are twofold. Maybe I can start with the second one, which is based on what I said in the prologue. In the prologue, I used more or less separation of variables to solve my Schrödinger equation, or to look at harmonic functions. So warped product is a natural setting to solve equations by separation of variables. And the other one is related to the limitation I was mentioning, is that this is more or less also the correct setting to have what is known as limiting Carleman weights. This is not exactly true, at least locally. Manifolds with limiting weights should look like that. and we have a global assumption on the structure. Okay? I think that one of the difficulties of the problem, and this is also related to the partial data problem, is that it is not really understood how the local features apply in this problem. So you have to solve equations globally, and that is part of the difficulty in the problem. Okay, so let me talk a little bit about the limiting weights and why they appear naturally. So it's maybe a good point to remind you that in the green formula, the important object is the product of solutions to Schrödinger equations. Okay. And then, so what you're looking is at solutions. Maybe I can write. Okay, so you want to find solutions of this equation. And the complex geometrical optic method is to look at solution. So here, I'm sorry, I'm going to change slightly notations. I'm going to have a small parameter, which is h, which is going to be tau minus 1 in the prologue. Okay? So if you look at the solutions I showed you in the introduction, they look like something like that: an exponential factor, an oscillating one, and then some amplitude that you can compute. And then what you want to get is some. So this will give you an approximate solution, and you want to construct a correction term which is small with respect to the parameter, such that this is a solution, an exact solution to the Schrödinger equation. So in particular, because of the presence of this exponential factor, if you want to find this remainder here, or with good decay property, well then obviously you have to solve an equation of this form. And then some, I guess here, I can write here. Then some source term which is going to be small because you have an approximate solution, which is just going to be, well, the operator acting on this guy. So if you put the exponential on the other side here, this is the kind of equation that you have to solve here. Find an R given an F with good estimates of R in terms of F, so that you get this guy here. Okay? So if you look at this operator, this is known as the conjugated operator because you conjugate by the exponential weight. This is P phi. And the particularity of this operator is a semi-classical operator. It depends on a parameter, and you want bounds sort of uniform with respect to the parameter h. So you have to be careful with the presence of this parameter. And the other thing is that it's non-self-adjoint. If you compute the adjoint, well, it exchanges the exponential. And so if you look at the adjoint, this is just changing the weight phi by minus phi. Okay? So what you're interested in is trying to solve equations with non-self-adjoint operators and having good estimates. So what you're interested in is in the solvability of such equations. Well, it turns out that in the non-self-adjoint case, this is more complicated to find solutions. And in fact, it is not always possible. So there's a counter example due to Hans Lewy that showed that there are non-self-adjoint operators which are non-solvable. So in the 60s, Hörmander derived a necessary condition to have solvability. And that is, so here my P is my P phi. You look at the symbol of this operator, take the Poisson bracket. So this is also the Poisson bracket between the real and the imaginary part. And you have to have a sign on the characteristic set of the operator. Okay? So in particular, so solvability, of course, by duality is sort of equivalent to having, well, is roughly speaking equivalent to having some a priori estimate, and these are known as Carleman estimates because there's an exponential weight with a parameter. And the estimate is true only if the sign is positive on the characteristic set, okay? Just going by duality. So remember that we are looking at products of such solutions, and we want to cancel the exponential behavior because we want to pass to the limit when tau goes to infinity or h tends to 0. Okay? So that means that you need this Poisson bracket to be positive, both for solution with a plus here in the phi and with a minus. And as we saw, it changes. Well, I mean, you can do the computation, and what you see is that when you change the sign of the weight, it changes the sign of the Poisson bracket. So the only option which remains is that this has to be 0. Okay? And in the case of the Laplace-Beltrami operator, you can actually explicitly compute the principal symbol of this operator. It's just a norm with respect to the metric. There's a G missing here. And then because it's a non-self-adjoint operator, there's a real part and an imaginary part. And if you look at the characteristic set, this is a sphere in the So this is the reason why you need this notion of limiting Carleman weights, and those are those weights for which this Poisson bracket is 0 on the characteristic set. So this is called limiting because the usual Carleman weights which are used in unique continuation, you usually expect this to have a sign here, a strict sign. And this notion was introduced by Koenig, Sjöstrand and Ullmann to study the partial data problem. So in particular, this log radial function, the t variable is a limiting weight. So the question is, well, if you have a manifold, is it always true that you have limiting weights? So in dimension 2, it is fortunate that it is actually true, and these are just harmonic functions. But in higher dimensions, there's a geometric characterization, which I've written here, but which you can think of that locally the metric is conformal. There's always this conformal invariance. The metric has to be conformal to a product. Okay? And so here comes in the product or the warp product structure. So this is why we have to have this structure, is to have natural limiting weights. There are nice, interesting things about limiting weights, geometrical features that we have studied. So in the warped products, you can unwarp things, as in the Euclidean setting. When you're taking the log of the radial function, you're actually unwarping a warped product. And the way you do that, because of the conformal invariant, is you can put the exponential factor in the t variable, change variable, and then you obtain something which is conformal now to a product. There is no warping term here. Okay? So this is the case in which I will put myself, is the case of a product. So now t will be the s variable. And in this structure, a natural limiting Carleman weight is just the Euclidean variable t, or s in that setting. Okay? So this is just a slide to formalize what I was saying in the prologue. So now I'm going to look at the transversal part of this product, so the M0 part, and you can define the geodesic ray transform. So you look at so this is points on the boundary of the manifold, and this is some direction which is ingoing. And the geodesic ray transform is just you integrate a function on the corresponding geodesic. So here the gamma is just the exponential map, okay? And between the time. So obviously, if you want to make sense out of that, you need to work with non-trapping manifolds. But let me just skip this part. Okay, and as I said in the introduction, in the simple case, you know this manifold to be injective. So that's interesting. But there are So it's an open problem to know whether this transform is injective in a more general setting, for instance, non-trapping manifold with a convex boundary. But there's a recent, result of Ullmann and Vaschi where they could prove the injectivity of the geodesic ray transform on manifolds which are foliated by strictly convex hypersurfaces. So there are now other examples of manifolds where you have the injectivity of the ray transform. And also there are some results when you are close to a real analytic manifold. Okay, and this is important because, as I said, the transform you will get at the end is some Fourier transform in the Euclidean variable and the geodesic ray transform in the curved part of on the transversal manifold. So what we were able to prove with Koenig, Salo, and Ullmann was assuming that the transversal manifold is simple. Then we could, and has this word product structure, then we could prove that the potentials are equal. In the work I'm talking about, we could improve this construction in the following sense. So you take a compact manifold which has this word product structure with an Euclidean part. You know that the Dirichlet to Neumann map with respect to two Schrödinger equations with two potentials are equal. Then what you will get is that the potentials are equal provided you know that the rate transform in the transversal manifold is injective. And that means in particular, of course, the simple case, but also the cases covered by the Ullmann and Vaschi results. So the difference is in the construction of the complex geometrical optics solutions. We were able to consider the case where you have caustic points and when the manifolds are non-simple. And I don't know, I don't remember when I started, so I have 5 minutes? 5 minutes, okay. So maybe I have a slight time. Okay, and then of course it also covers the case where you try to recover a conformal factor if you have the same structure on the metric and if you know the injectivity of the ray transform in the transversal manifold. So now I'm going to redo a little bit the construction that I did in the Euclidean case, but in the curved setting. And so it's going to be look very similar. So I'm going to look at solutions which are products. So this is this Euclidean variable. In the introduction was the log variable, the log radial variable. And in our setting is just the Euclidean part after unwarping the product. And so if you look at the Laplace operator with the product structure, what you obtain is just this operator, which looks a little bit like the wave operator if you've changed t in it, if you have complex time somehow. And there are relations also with the wave equation. So what you take is for W is a solution to this equation here, and this means exactly as in the prologue, this exponential weight with a complex parameter which is the same as in the introduction one, which is tau plus I lambda or h minus 1 plus I lambda. So extremely, well, exponentially increasing or decaying when this parameter is large, and also oscillating with respect to another parameter. Okay, and if you want to have an exact solution, well, you want to have a solution of this equation. And as I said in the introduction, it actually suffices to have approximate solutions there. So how do you go from approximate solutions to exact solutions? Well, you look at this equation and you derive a priori estimates, and then it's a classical argument by Hahn-Banach, which allows you to have solvability. So these estimates, as I said, are Carleman estimates and were derived in the to deal with unique continuation problems. So they look like that in our setting. So you can forget about this term, but you control the L2 norm by this, which is going to be small if you take W to be an approximate solution, and what you gain is 1 power of the real part. Okay? So this will tell you that this will be small when this is bounded. Okay? So with this Carleman estimate and the Hahn-Banach theorem, you can actually construct solutions which are of the form that I showed you in the introduction, so some exponential and some Quasimode. Here, this is the Quasimode. You can actually take something even worse than what I said in the introduction, and some remainder term, which is now just small. Maybe there's something missing here. Okay. So if you do that, and exactly as I said in the beginning of this talk, if you take two solutions with opposite exponential behavior, look at the products, U1, U2, what you get is this oscillating factor times the product of two Quasimodes here. And so if you compute, this is exactly what you get. So you get some, as in the beginning, some Fourier transform with respect to the Euclidean variable, and then you have to understand the limit of this guy when the parameters tau goes to infinity or h tends to 0. Okay, so let me just show you very quickly maybe how you can. So there are two ways of construct. So the whole question now is to construct those Quasimodes and understand the limit. And maybe the quickest one is the microlocal approach. So this is very sketchy. You have to do more than that. But the way you do it, first of all, you can always reduce to the case where lambda is 0. So here I'm taking my complex parameter s to be just h minus 1. So what you obtain, if you factorize the operator, is you have to find the solutions to this Quasimode for this operator. And so what you can do is find two Fourier integral operators which send this operator to just the derivative with respect to one variable. Okay. So as I said, this is sketchy. This is not exactly true, but so then it's very easy to find a Quasimode. It's just you have to take something whose derivative is bounded with respect to the first variable. So what you can take, for instance, is 1 and any function in the other variables than x1. Okay, and then you use this Fourier integral operator to go to the manifold. So you have a sort of dictionary between locally, let's say, between the manifold and some Euclidean setting, and this operator and the operator of derivation with respect to one variable. And so what you take for WH is just a usual wave packet, so something which concentrates in space and frequency close to 1 point. So if you look at the kind of integral that we're interested in, so think of this as the Q function here. By the Egorov theorem, you can actually put the action of the integral operator on this operator. So A here you have to think of it as a multiplication by the Q by the potential function. So what you obtain after conjugation is the Q function, which has been composed with a diffeomorphism, which is just the action of the geodesic flow, and then some terms here. And then when you pass to the limit, you have some remainder lower order terms which disappear. So when you take the limit here, when h to 0, what you get is this integral here. And this actually shows that you can, so the functions I've constructed here are functions which are actually concentrate on geodesics. Okay, so in the Euclidean setting, the geodesic is just a straight line. So this is what you can obtain. And I think it's time for me to finish. Sorry. Thank you.